Okay, it's 7:30 and we're going to get started. Welcome to the July meeting of the Johnson Space Center Astronomical Society. I'm Doug Holland, the president of JSCAS, and this is our agenda for this evening. If you have questions and comments for our presenters, you can either put them as a YouTube comment, if you have an account that will let you put in YouTube comments, or you can email your questions or comments to the email at the bottom of the slide, jscaslive@gmail.com. Trevor Quinn will be gathering up those comments and questions and providing them to our presenters. So we have three things on our agenda this evening. We have Galileo's Toes with Dr. Aaron Clevenson. Then I will be doing a DIY astronomy on telescope mount improvements. And we'll wrap it up with Star Party News with David Haviland. So before our main speaker gets started, I would like to tell you a little bit about him. Dr. Aaron Clevenson is a past president of the North Houston Astronomy Club and past chair of Houston's Astronomy Day. Aaron has taught stellar and planetary astronomy at Lone Star College in Montgomery for 16 years. He wrote the astronomy textbook that they use, which is provided free to the students. He is the Observatory Director at the Insperity Observatory in Humble. Aaron is an observing program director with the Astronomical League and coordinates their Master Observer progression, in which he is one of 3 Platinum Master Observers. He remembers his first astronomy experience at 6 years old when his sister built him a solar observatory from a cardboard refrigerator box with which he saw a partial solar eclipse through a pinhole projection. His interest and goal in astronomy is to see it all. He is here today to share with us one small corner of it all. So with that, I'd like to turn it over to Dr. Aaron Clevenson.
Dr. Clevenson, you have a go.
Okay, thank you very much. Good to be with you all again. It's been a while since I gave a presentation to you all, and I'm very excited about that, and thanks for having me. Tonight, I wanted to talk a little bit about something I call Galileo's Toes. We'll get into that and talk about all of the details of what that means, and hopefully some opportunities for you to go out and do some additional observation and exploring. So, got to start with giving a little bit of credit to the man himself. So, Galileo Galilei, born many, many years ago. So, what's this, about 400 years ago? And he is the person who gets credit for being the first person to actually use a telescope to do some observations of celestial objects. And he observed some really cool stuff. And for example, mountains on the moon, Jupiter's moons, sunspots, and phases of Venus. And some of these played a significant role in how we view astronomy today. For example, Jupiter's moons was concrete evidence that everything doesn't orbit the Earth. So they used to think the Earth was the center of the universe and everything orbited it. And the moons of Jupiter, no question about it, were orbiting Jupiter. And so that kind of punched a hole in Aristotle's view of the universe. But the real thing that kind of put the nail in the coffin for the geocentric model and led the way for the heliocentric model was the phases of Venus. Because who would have thought? But he observed the phases of Venus, and he recognized that it took about 18 months to go through a full set of phases. And he compared that to the moon, which takes a month, and that meant Venus had to be much further away than they thought it was. And as a result, it couldn't be that far away. There had to be another reason. And that other reason, of course, is that Venus orbits the sun. It doesn't orbit Earth. So what are the toes? Well, he discovered the 4 largest moons. Actually, initially, he only discovered 3, but ultimately he saw the 4th one. We do call them Galilean moons because he discovered them. And normally they would interact with Jupiter. And so it happens most of the time, pretty much every apparition of Jupiter, we get to see this dance between the planet and the moons. And there are 4 different types of interactions that can happen. So we can have transits, that's the T in toes, of Jupiter's moons going across the face of Jupiter. We have occultations, when one of the moons actually physically, from our perspective, goes behind Jupiter. Eclipses, which are Jupiter's moons going into the shadow of Jupiter. So that's a little bit different. Not physically behind the planet necessarily, but in the shadow of Jupiter. And then shadow transits, which are like transits, except it's the shadow of the moon. So the moon's going to pass in front of it. It gets between the sun and Jupiter, and it casts a shadow on the planet itself. So 4 different things: TOES, transits, occultations, eclipses, and shadow transits. So I want to start out by defining some of these terms just to make sure we're all on the same page. Most of you are experienced astronomers, so you know all about this stuff, but let me go ahead and do it anyway. So transit is the passage of a celestial body going over the meridian of a place or through the field of a telescope. So that's an official definition. Astronomers use it a little bit differently. We usually mean crossing the center of something, but then we take it and we extend it to the whole passage. So some examples would be Mercury or Venus, because they're inner planets, occasionally transit the face of the sun. So the transit itself is actually crossing that meridian, but we view the whole thing as the transit. Stars can cross the meridian over our head, and so a lot of our telescopes that are, if you have one that's permanently mounted, it cares about when things are going to transit or go cross that line from the north to south. And then the last one, the one that's relevant to us, is Jupiter's moons crossing the face of Jupiter. And then, of course, shadow transits are basically the same thing as a regular transit, except it's actually the shadow. And we've got some things that will show these in a little bit more detail. The second one is occultations. It has nothing to do with the devil. But basically, to occult something is to shut it off from our view or exposure. So in other words, we can't see it anymore because it goes behind it. Astronomers use it to mean physically passing behind something else. So examples would be a solar eclipse, which of course will also show up under eclipses. The Earth's moon passing in front of stars, asteroids, or planets. An asteroid passing in front of a star. So both of those are occultations that the International Occultation Timing Association, IOTA, would be very much interested in having you guys do some of those, because they're always looking for more data. And again, as it relates to us, it would be Jupiter blocking our view of one of its moons. Third choice would be an eclipse. And there's 2 different types of eclipses. So one of them is the total or partial obscuring of one celestial body by another. So that's normally what we would think of as an eclipse. But it could also be the passing into the shadow of a celestial body. And so different ones are different forms of that. We use it to mean physically passing behind something else, or we can also mean passing into the shadow of something else. So it disappears even though it's actually still there. So some examples: a solar eclipse. That's the first definition, where the sun is actually completely behind the moon. Lunar eclipse, which is the second definition, where Earth's shadow blocks the sunlight and that light doesn't get to the moon. So the moon, in our case, usually it turns red, but basically it's not getting direct sunlight. And then again, in our case, Jupiter's shadow blocking sunlight from reaching the moons. That's also definition 2. That's what we're going to talk about today. So the Galilean moons, there are 4 of them. I want to thank NASA for the wonderful pictures. Any that aren't labeled are mine, but the ones that are labeled are from NASA. So these are the 4 moons in the order from closest to Jupiter moving outward. Io, which is famous for its wonderful plumes of sulfur-based volcanoes. The largest volcano eruptions that we've seen anywhere in the solar system. Europa, which is an ice ball, basically, and it is believed to have subterranean, well, let's call it subsurface liquid saltwater oceans, which is very exciting if you're looking for life. Ganymede, which is the largest moon in the whole solar system, also has subsurface liquid saltwater oceans, which is another exciting place to look. And then Callisto, which is the oddball of the bunch, because unlike the first 3, which look very much like planets, they have layers, they have a core, a mantle, and a crust, Callisto seems to be more like a jumble of rock. So very different. But these are the order they're in. Most of them are tidally locked to Jupiter, so their orbits are very predictable and related to each other. So let's talk about the 4 different types of things, the TOEs. So the first of the toes are transits. And this is a picture of Jupiter. I believe that's Io getting ready to start moving across the face of Jupiter. And the moon passes in front of Jupiter. It's really hard to see usually because the moons are normally about the same color as the surface. So they're hard to pick out unless you actually see them and follow them. But not a whole lot of contrast. The second one are occultations. And in our case, this is another example of a moon. This is a fake image, by the way. Jupiter is real, but I couldn't find a really good occultation image to use. So that is a moon, but this is a combined picture. And in the case of an occultation, again, the moon passes directly behind the planet. So from our perspective, the shadow is not a player in this at all. It's just the moon's there. Jupiter's moving, the moon's moving, and eventually the moon goes behind Jupiter. So it vanishes when it reaches the edge of the planet. Eclipses are a little bit different, though, when we're talking about the moons. And so if you follow the red arrow here, you say, hey, the moon disappeared. It's not there anymore. And that's because the sun would be off to the right, and that sunlight is causing a shadow, and we can't see it, but the shadow is in our view. And when the moon moves into that shadow, it disappears. So it tends to disappear before it reaches the edge of the planet itself. The fourth one, and the last one of the toes, is a shadow transit. And this, to me, is really one of the coolest ones. It's not real obvious here, but when these happen, you get what looks like an almost perfectly round black dot moving across the face of Jupiter. And again, this would be Io with its shadow on the planet. And depends on where the sun is. So in this case, the sun has to be off to the left-hand side. And a little bit later, I would guess 5 or 10 minutes later from the time this picture is shown, it would be in transit as well as shadow transit. So often they come in pairs. I've got to stop here just briefly. I don't have a picture of it, although I do somewhere at the observatory. But on one occasion, we were observing Jupiter, and the shadow of Io was right in the middle of the Great Red Spot. And we got to watch it most of the transit. As the Great Red Spot moved across the planet, so did the shadow of Io. It was just amazing. Amazing to see. So why does this happen? Yeah, what's the mechanics behind this? Well, in general, it's pretty straightforward. And if you've watched the moons, they're not in a perfect line. This picture makes it look like they're very much in a straight line, but they're not. So when they get real close to each other, they don't always go in front of each other. Sometimes they miss a little. But they seem to go back and forth as Jupiter orbits the sun. We watch them, and they do this dance. And as they do that, part of that orbit takes them in front of or behind Jupiter. And so when they do that, we get to see these different events, Galileo's toes. And if we take a look at these in a little bit more detail here, what we see is in this drawing, by the way, this is not drawn to scale of any kind. Jupiter is here. It's lit by the sun. And the Earth is off at some other position in our orbit. So we get to see Jupiter. This would be awfully close to evening, I would believe. So this would not be a good time to be looking at Jupiter, but we get to see Jupiter. And when that's the case, you get this kind of an arrangement where you get the sunlight coming in, you get our line of sight, which is the blue arrow, and you'll notice Jupiter's shadow I've shown on here going out behind Jupiter away from the sun. So if you take a look at this picture, what you see is, okay, there are going to be times when those moons are going to be passing in front of us, passing in front of the sun, passing behind Jupiter, and also passing into Jupiter's shadow. So this is the mechanics. This is the foundation for where these Galileo's toes come into play. So what is one of the possibilities? So the first one is the transit. So we have a Jupiter's moon in transit. In this case, transit means we can see the moon in front of Jupiter. So the moon is orbiting Jupiter. As it comes around, it passes in front of us. And it's lit, Jupiter's lit, so we get to see both of them. But as I mentioned earlier, they're very similar in color, so they're hard to tell apart. But when it passes between us and Jupiter, we see it as a transit. Occultation, same kind of thing. And in this case, Jupiter's moon has moved around past the sun, and now it's getting ready to go. Actually, it's already behind Jupiter. And so when it passes behind Jupiter, the light from the moon disappears. We still get to see Jupiter, but we no longer see the moon. So that would be the occultation, the O. An eclipse is caused by the shadow of Jupiter. So now the moon has moved a little bit further on, and now it's in the shadow of Jupiter, kind of in a direct line from the sun, so sunlight can't get to it. And in this case, we wouldn't have seen it go into eclipse, but we will see it when it comes out, when it moves up around where my cursor is up here. We'll actually get to see it come out of eclipse. And then the last one is the shadow transit. And so in this case, we're not perfectly lined up, but again, the moon is lined up with the sun and Jupiter. And so the sunlight comes, it hits the planet, and because of the closeness of the moon to the planet, we get this dark spot on Jupiter. And again, nothing is to scale here, but these are really cool because it's just such a stark contrast. You can really make out the shadow very clearly. So one of my favorite of the 4 toes. So how many toes did Galileo have? Well, if you think about it, there are 4 Galilean moons, Io, Europa, Ganymede, and Callisto. And there are 4 significant events, right? Transits, occultations, eclipses, and shadow transits. And then, of course, they all have beginnings and ends, right? Ingress and egress. And so if you take those, it's 4 times 4 times 2, you get 32 different events. So he has 32 toes on his right foot. So lots of things to look for there. They're not all visible every time we have an apparition of Jupiter, which is about once a year. But you don't get to see them all because they may not be perfectly lined up to actually show us all of these things. And then you also have to take into account daylight. Some of them happen when it would be daylight for us, so we don't get to see them at that time. But what about the other foot? So we've been talking about Galileo's toes, and we've been talking about these 4 different things that can happen between the moons and the planet itself. But twice in each of Jupiter's orbits, the alignment of the plane of the moons as they orbit Jupiter align perfectly with the Earth's orbit around the sun. And when this happens, you get mutual events. You get events where the moons interact with each other. And so these are really cool. By the way, this is the year. So you need to get out there and observe these. We'll talk about that in a little bit. If you look at what is a Jupiter year, it's almost, let's call it 12 years, 12 Earth years. That means every 6 years this happens. So if you miss it this time, it'll be 6 years before you get to do it again. But it lines up perfectly. And then you get to see events where the moons actually interact with each other. So it is close to perfect. It's wonderful. They're, as I said, they're called mutual events. And oh, by the way, did I mention this is the year? So you all really need to go out and do at least one of these just so you can say you've done one. But it's wonderful. So this is Galileo's toes. I refer to it as on steroids because these are really exciting. So what are we talking about? Well, there's 2 kinds, occultations or eclipses. And I find it interesting that the source that I used to get some information broke them up into total, partial, and annular. So that's kind of like a solar eclipse, right? You can have a total solar eclipse where the sun disappears. You can have a partial where there's a bite taken out of it by the moon. Or in the case where the sun is either too close or the moon is too far away from us. Remember, everybody's orbiting in ellipses. So when that happens, the moon's too small to cover up the sun and you get an annular eclipse. Well, the same things can happen between these 2 moons. Now, not all of them, because keep in mind, some of them, the moon's too small to actually physically cover up the bigger moon. But that would be like Io trying to cover up Ganymede. Just way too big a size difference. So there are 6. We're not going to count them. We're only going to count 2, occultations and eclipses. But these are the drawings of what's happening. The color of the arrow represents which of the moons is moving. So in this case, the bigger moon is moving. Doesn't quite cover it up, so it's a partial, and it's an occultation. In the next one, the orange planet is actually gray in this picture because it's completely covered up by the blue planet, or the blue moon rather. We can't see it at all. And then in the third one, it's actually, I think it's wrong, but that's all right. We'll keep going anyway. In the third case, the smaller planet is trying to actually cover up the bigger planet. And what happens is you get an annular occultation, annular being ring. And that's that ring around it of the bigger planet. You can see it around the smaller planet. Now, I do need to stop here and just mention this is the perfect scenario. And in my backyard telescope, I cannot see these. In fact, at the observatory, I can't see that level of detail. I can see the occultation, and I like to record it. We'll talk about that in a minute too. But as far as actually seeing two moons and telling which moon is which and actually seeing a smaller moon on the bigger moon, that's even more difficult than trying to see them on the face of Jupiter. So I've never seen that, and I'm not sure you could do it in a backyard telescope. The third set are eclipses. So to do an eclipse, you have to have a shadow, and it's the shadow that matters. So a partial eclipse, this is a partial eclipse of the orange moon doing the eclipse of the blue moon, and the shadow takes a bite out of it. The second one would be where, and we switched moons now, so it's the bigger moon is so big that its shadow is able to cover up and completely block out the smaller moon, excuse me. And then the third case is the annular one again, where the shadow is small enough that it basically covers up the center or some other portion of the larger moon. So theoretically, there are 6. Again, we're only going to worry about 2, the occultations and eclipses. And I got a couple pictures here. The one on the left, obviously, is a partial occultation, and the one on the right is a partial eclipse. And these are Io being caused by Europa. So these are the kind of things you might see. Like I said, I've never seen quite this level of detail in my telescopes, but conceivably it's possible. Okay, so how many mutual events are there? Well, again, there are 4 Galilean moons, and each of those moons can interact with every other one of the moons. And then there are 2 types of events. We're going to use the occultations and the eclipses. And as I said before, we're not going to worry about the total, partial, and annular. I think that's just way too much for life's too short to worry about that. So we get 4 times 3 times 2, 24 different events. So he obviously has 24 toes on his left foot. So those are the 2 main things I want to talk about. Again, this is the year to do these, so I hope you all will get out there and at least give one of them a try. How do I observe them? I want to give you a little bit of detail there. So if you have a modest telescope, you can see them fairly well in your eyepiece. I'm a visual observer for the most part, so that's the way I like to see things. But what I discovered was I wasn't getting the detail that I wanted. I could see they were interacting and they kind of merge and disappear, and I now only see 1 moon when I used to see 2, but I'm not seeing the level of detail I would like. So I do nod here that you probably can see them in stabilized binoculars because you can see the moons, but again, they were going to be at that level. You won't be able to see all the detail you might want to see. So what I do to get accurate timings, you need to record them. And so I use a video camera, but you can also use a very fast still camera like a ZWO camera. We've never done that with it, but we should. The reason for that is if you want real critical timings, the video camera, you can do a time insertion and there's a time printed on every frame of that video. So you know exactly what time it is. And if you want real accurate timing, you need to do that because the timestamp that you get when it actually downloads a still image is not necessarily going to be accurate out there in the milliseconds. So the timestamps are very important, very critical. So what I do is I capture the video. The recommendation at the time was, oh, and you want to put it on a VCR, don't try to do it digitally. I'm not sure that's still the case, but we do still do it that way. We bring it down to a VCR. I just love archaic technology. And then it's really important to use software to load it onto the computer, but you want to use software that's not going to drop any frames. It's critical you get every frame if you're doing timing. And so we use virtual dub with a Huffy UV video compression, which theoretically doesn't drop any frames. It does drop a few, and it tells you how many it drops. So you get an idea of how good your data is. And of course, there's a timestamp on every one of those frames. So you can actually tell if the frame is there when that frame was taken. And then we take that video that's now on the computer and we analyze those images using a tool called LiMovie, which lets us export something we can put into Excel, and then we can print cutesy graphs. And so we can actually see the dimming of the object, in this case two objects, when they combine. So here's an example of what one of those might look like. And it's a little bit noisy, but basically what you're doing is you're looking and you set it up so that when you do the analysis, you're looking at both moons as they approach each other. And when they get to the point where they combine, you get a dip. And the side of this dip is the partial. If it does go to total, that would be down here at the bottom where it hits total, and then it goes back to partial again until you can actually see both of them. So this horizontal part of this picture is where you're actually seeing the light from both moons. And we do the same types of things when we're doing occultations of asteroids and things like that. So works really well. We've been very pleased with it. We haven't done it in quite a while. And that's largely what I want to talk about tonight, but I also want to take a little bit of time here to talk about the Astronomical League.
Dr. Clevenson?
Yes?
Can we interrupt you for a couple of questions real quick?
Yeah, please do.
Okay. The first one, do the oppositely spinning bands on Jupiter impact its moon's orbital paths when they cross Jupiter's lunar ecliptic planes?
All right, so you can't tell, but I'm sitting here thinking about the answer. So the bands do not, because the moons are far enough away that they don't actually interact with Jupiter itself. Jupiter's gravity certainly has an effect, but to the best of my knowledge, the bands and features on the surface of Jupiter don't have an impact.
All right. Next question. What is a good reference to tell the dates and times of these Jupiter events?
So I don't have it, unfortunately. I went searching for it and I could not find the one I've used in the past. So apparently they have taken it down. There is a person, actually a group of people, who are very much interested in the mutual events. And at one point they actually thought they could tell that let me see if I can remember who it was. I think it was Ganymede. They could tell that Ganymede actually had an atmosphere. And of course, nobody believed them because you can't do that from Earth. But they could actually detect it in the way that the curve, the light curve, similar to the one we're looking at, changed as the other planet went in front of it. And so there is a group doing that. I can get additional information and I will provide that to y'all, but I couldn't find it for tonight. For the regular events, my standard go-to is Sky and Telescope. Their website has a list of Jupiter's events with its moons, and I find that to be a very good source.
Okay. Another one, where do you suggest getting the timing gear? I've looked on IOTA for regular occultation, but nothing using current technology.
So, so yes, I was going to send you to IOTA. So what I have found is the original time insertion device was from, I think it was New Zealand, and the guy who created it stopped selling them. He just shut up his shop. And so the original is gone. It took them a number of years, but eventually they came out with an IOTA device, so one that they're selling. It does time insertion, but as you mentioned, it's designed to work with a VCR. So it's not current technology in that sense. And again, their concern at the time, I haven't talked to them lately, but their concern at the time was losing frames. And even the best direct-to-digital tools at that time, so this was a while ago, but at that time, we're dropping frames. And that's no good if you're trying to do real accurate timing. So that's my recommendation.
Okay. I think we've got two more real quick.
Go for it.
One, could you explain how Jupiter's moon was used to calculate the speed of light?
No. Sorry
Okay.
for the real quick answer there, but no, I am not familiar with that at all.
Okay. I've got, now there's another one that's come in. I've got a question for myself. Do the orbits of the moons ever coincide to where you get shadow transits of two moons simultaneously?
Absolutely. It happens a couple times a year. So it's not real frequent because they have to be in just the right place. And of course, Jupiter has to be at the right orientation relative to the sun for us to get good shadow transits. And conceivably, you could have three. I've never seen a three. I have seen twos a number of times. And the three is conceivably possible, but they're very, very rare. And so I've never actually seen one of those. I keep watching, keep hoping, and we'll catch one someday. And I would say 4, the odds are just so minor that you'll never see one.
All right. And one final one, and then we'll let you continue.
Okay.
If this light curve is similar to how exoplanets are discovered, could we find atmospheres in a similar way to how they found atmosphere on Jupiter's moon?
And the answer to that has to be yes. However, the problem is Jupiter's moons are relatively fairly bright. And so when they pass in front of each other or interact with anything, you could do the same thing passing in front of a distant asteroid or something if it happened as well, or a star. But when you start talking about exoplanets or extrasolar planets, you're talking about such a tiny little dip that although you can catch that dip on a home telescope, I think it would be really, really difficult to be able to detect the atmosphere. So is that it?
That's it. Please continue.
Okay.
Thank you.
All right. Yeah, no problem. And if there are more questions, that's great. We can take another question period. I've only got a couple more slides. Okay, so let me talk a little bit about the Astronomical League. So I know as a club, the club is not part of the Astronomical League, and I understand all that. But I know many of you may be, and I want to provide you an opportunity to consider, well, hey, maybe there's some things out there that I would like to take advantage of. So I do know that some of you are members through other clubs in the Houston area, and that's great. If you are part of another club, then you are part of the Astronomical League. But we have 3 things directly related to this talk that I did want to mention. And of course, we can't send you a certificate, but what it does mean is you can go out there and look and see what we're offering, and the lists are out there and public. So you can go out there and get to those lists, and you can do them if you want. We can't stop you from doing it. In fact, we want to encourage that. So the first one is we do have a Galileo's Toes certificate. Sadly, I have to admit I have not earned it yet. And my reasoning is some of the Callisto events have not happened when I could see them. So I've missed those events, and I'm just waiting, biding my time. Sooner or later, I'll catch them. The second one created on top of that is Galileo's Toes 2, excuse me. And this is the mutual events between the Galilean moons. And that one I've done a few, but I have a long way to go on that one. So I'm hoping this is the year for that, and I'll catch a bunch of them, and hopefully I'll be able to complete that certificate myself. But they're basically what we talked about, the different events, the 32 or the 24, and the goal is to see as many of them as you can, ideally all of them. The third one I want to mention, though, is something that they're doing special this year. So some of you don't care about the why they're doing it, but it's the 75th anniversary for the Astronomical League. And they came to me and they said, we want an observing program. And I said, okay. And I looked at it and said, well, this is the year for Jupiter. And so maybe we ought to take advantage of that. And they said, we need 75 observing challenges. So I got together with some of my experts that I know who are very knowledgeable about Jupiter. And we came up with a list of 75 observations. I think they're fairly challenging. They don't have to be done through imaging, but I think it would be much easier to do them through imaging. And Jupiter has just now come into the evening sky. It's rising a little bit before midnight. So for those of us that are evening astronomers, we're getting into that season. And so now's a good time to start observing, at least in my mind. So if you want more information on these or anything else at the Astronomical League, their website is at the bottom, astroleague.org. And I give you the 2 additional steps if you want to go out there and take a look at these observing programs. So you go out to observe, it's a drop down at the top. And off that list, you then pick observing programs alphabetically. I left that word off. And that'll bring you into our observing programs. And in case any of you haven't gone out there and checked lately, we have over 75 of them at this time. So there literally is something for everybody, no matter what your interest or experience level. And if anybody's interested in more information, then I do have lots of information because, as was mentioned, I'm one of the observing program directors. And I think that's it. So good luck. I hope you all will go out and do some observing on some of these different opportunities related to Jupiter and Galileo's toes. Before I do potentially sign off here, I had 2 other things I wanted to mention. The first one is, it was mentioned that I created the textbook that we use at the observatory, and my email is down here at the bottom of this screen. So if any of you would like access to that, it's electronic, but it is a full-blown introductory textbook. I will let you have access to it. Just send me an email, and you can have that. It is free. I give it free to my students. The second thing I wanted to mention, and I've probably mentioned this at some previous gathering, but the Astronomical League does have one program that's available to anybody, anywhere, free. And so it's designed for students or children that are 10 years or younger. So if you have any children, grandchildren, neighbors, a class, anything else you'd like to do, it's called Sky Puppy. And it's an intro program designed to get the youngsters, 10 and under, involved in astronomy and interested in our hobby. Because I've heard people comment that we are a graying hobby, and I think that's wrong. We are a gray hobby. We're not turning gray, we are gray. And I think part of that is you have to reach a point in your life where you can afford the time and money to do astronomy. And what I think we need to do is get the youth involved, because those are our future astronomers. And when they get gray, they may find themselves in a place in their life where they can actually do astronomy. And if we can introduce them and hook them now, they'll be ready to do astronomy when they get to the point where they can. That's what happened to me, referencing my 7-year-old experience with my solar observatory. And it took me till I was 45 to get to the point where I could actually do it. Okay, so again, textbook, Sky Puppy, just send me an email. Are there any other questions?
We have one more. Can you tell us when the public times are at the Insperity Observatory?
Right. So unlike HAS, the Houston Astronomical Society, you guys could come if you are available. We're open on the first Friday of every month from sunset to 10 p.m. So it varies through the year. During the summer, it's typically 8:30, but during the winter, it's sometimes as early as 5:30. Those are really long nights. And we'd love to have you all come. No reservations required. And we are open for business. We've, to a large extent, gotten over the COVID situation. All of my astronomers have been inoculated, so we feel fairly safe. We do encourage people to wear masks, and half of the folks do.
All right, thank you. I'm going to turn it back over to Doug.
Okay.
Doug, you have a go.
All right, Aaron, thank you very much for that very interesting talk, and thank you for being our speaker this evening. Next up, DIY Astronomy, Telescope Mount Improvement. I'll be doing this one. So in the world of astrophotography, there's a lot of things that can go wrong, but luckily, everything we need to know is documented in the handbook, Basics of Astrophotography. And here's a picture of Volume 1 of Basics of Astrophotography, and you can go and check that out at your local library. Okay, So one of the most important components in astrophotography is your telescope mount. And the reason it's important is because if you take an average telescope focal length and average pixel size of a camera, it turns out that a pixel corresponds to about 1 arc second of angle in the sky. So an arc second, we'll review that real quickly. 1 degree has 60 arc minutes and 1 arc minute has 60 arc seconds. So within 1 degree in the sky, there's 3,600 arc seconds. So it's a fairly small portion of the sky, and it is a challenging thing to be able to get a mechanical system to point at this little small spot in the sky accurately and not deviate for long exposure pictures, which we take. Like, it's very common for astrophotography pictures to take 5, 10, or even 20, 30 minutes per exposure. And it's not a trivial problem to get a mechanical device to track the sky that well. So the mount that we're going to talk about tonight is Los Mandy G11, but these principles apply to other mounts too. The Los Mandy G11 is a German equatorial mount, and it has 2 axes. It has a declination axis here, and this gives you your north and south movement. It turns this way and it turns around this axis. And you have your right ascension axis along this axis, and that gives you your east and west movements. And as you're tracking the sky, you're going from the east to the west. So the issues that this particular mount had was the declination axis had stiction, which is a combination of the words static and friction, static friction. And it had some jerkiness when it was trying to move in the declination direction. You would get some jerkiness instead of a nice smooth movement. The other problem was the right ascension axis had periodic error, which I will define here in a minute, which was causing elongated stars and smeared images. Now, this telescope mount was actually built in 2005. I purchased it used in 2010, so it's about time for it to get a little work done to it. So first, we'll talk about the declination axis. As I told you, it had static friction, or stiction. And this mount is kind of nice in a way that you can actually take the declination axis off. There's 4 bolts here, and you can actually take this part of the mount off. This is the declination axis. And then by taking this nut off the bottom, you can pull the rod up through the middle, and you can disassemble this whole thing. It's fairly easy to take it apart. It turns out the problem that I had was that the thrust bearings were gummed up with old lubricant. So instead of acting as lubricant, they're acting more as adhesive. And this thrust bearing is this ring here and has these little rollers bearings all over it like this. And they're supposed to roll nice and smoothly and let the declination axis move back and forth very nice and gently. But instead, these were all gummed up, and so it was just grating and sticking. So this has several thrust bearings. It has a larger one, these larger ones here, and it also has some smaller ones down here. But they were all pretty much gummed up with the original lubricant that this telescope mount was made with. So to fix that, what I did is first step is to clean and degrease all the old lubricant off the thrust bearings. So I use Gunk general purpose degreaser. There's many degreasers out there, but this is one of them. When you use this degreaser, you can clean them off with like a old toothbrush or something like that. You need to have pretty good ventilation, because if this can melt off your old grease, you can imagine what it's going to do to your lungs. So you want to do it. I did it outside, but you want to do it within good ventilation. And it took the grease off very nicely. As you can see, this is a very clean thrust bearing over here after it's had the little grease taken off of it. Then to re-lubricate the pieces, I use a combination of super lube and tungsten disulfide powder. Okay, this combination, I used to work for NASA, and we gave a project to the University of Texas at Austin, the mechanical engineering group. We gave them a project to determine what was the best lubricant for stiction. And a group of students there built a test jig and to test stiction, and they tested all kinds of lubricants for us. And in the end, this combination of super lube, which is a Teflon-based lubricant, and tungsten disulfide was by far the best of any of them. And so that's what I used. And you put this back on all the parts where you took the old grease off, you reassemble it, and the end result was I had much improved stiction on the declination axis. Okay, the second axis, the right ascension axis had a problem with periodic error. So it caused the stars to be elongated and smeared images. But first we have to understand how the right ascension axis works. So this is the right ascension axis over here with the declination axis gone. This is just it all by itself. Now you have a motor, obviously. You got to have a motor to turn this thing. It's the DC servo motor. And then the motor is connected to a gearbox, which changes the amount of time it takes for the output of the gearbox to turn compared to the input with the motor. And it also changes the torque that's being applied. You actually increase your amount of torque by using a gearbox. So it changes the speed and also increases your torque. Then there's a device called an Oldham coupler that couples the gearbox to the worm gear. The reason you do this is because the motor and gearbox may not be perfectly aligned with the worm gear. And this device, which I'm going to show a close-up here in a minute, compensates for these not being perfectly aligned with each other. Then that connects to the worm gear, and you can see these threads on this worm gear, and as this turns around, it turns the ring gear, which is what makes the right ascension axis turn east to west to follow the rotation of the Earth. Now, I told you I was going to define periodic error. So periodic error is error that's caused, that is the change in speed of this ring gear over the period of one rotation of this worm gear. So the worm gear turns around, in my case, it turns around about once every 4 minutes. But because there's imperfections in the worm gear machining and the other mechanical devices associated with this worm gear, you'll see a periodic error. As it turns around, it'll slow down a little bit in some spots, and it'll speed up a little bit in other spots, and there'll be some jerkiness here and there. And it repeats itself in roughly the same pattern every 4 minutes. That's why it's called periodic. Okay, so the first step is disassemble, degrease, and lubricate all the right ascension axis components, just like I did with declination. And you can see this black grease on here. Use the same degreaser and the same lubricant that I used on the declination axis. I got this all cleaned up and degreased and then re-lubricated. The second step was I replaced the bearings. So inside these are called bearing blocks, these black cubicle looking things here. There's actually bearings inside there that hold the worm gear. And they look like, ball bearings with a hole in the middle, and they sit inside these bearing blocks. Now, I got a lot of ideas from looking at the Los Mandi users group, but a lot of the guys on that users group actually had very good luck with Boca Bearings, which is a great company in Florida that makes bearings, all kinds of wonderful things. And I got some Boca bearings. I also got some new Los Mandi bearings. I actually had better luck with the Los Mandi bearings than the Boca bearings, but other guys who have done this have had better luck with the Boca bearings. I actually busted some of the Boca bearings when I was doing this and went through quite a few of them. I actually wound up buying several sets of these, and I had trouble breaking them. They are ceramic bearings, I believe, and I think I was probably too rough with them. But in the end, I replaced the bearings. The old bearings were a little rough, and the new were super smooth. Number 3, this is actually what started this whole change that I made. I added a Belleville washer to the bearing block. So a Belleville washer is a washer that looks like this. It's concave, but it's actually being used like a spring. So what happens is this bearing block here is actually represented here, and it's also the same bearing block that's over here. It's not the one that's towards the motor, it's the one that's away from the motor. But the idea is you put some of these Belleville washers inside the bearing block. Here's the bearing, here's the worm gear. And this is going to act like a spring to put tension on the worm gear so that it holds tight in tension with the ring gear. This keeps the worm gear from moving back and forth as it's turning around, and gives a solid interface between the worm gear and the ring gear. And this is the thing that a lot of people in Los Mandi's users group felt like was the big thing to do to improve these mounts, and it did make a significant improvement. Now, this idea of trying to keep the worm gear from moving back and forth is actually not a new idea. If you look on in the Los Mandi manuals, they tell you when you put these blocks on here, you're supposed to hold them with your hands tight so that the worm gear doesn't move when you're tightening these blocks down. But no matter how tight you hold them, there's not going to be a lasting tension. But the springiness of this Belleville washer will give you a springiness that will keep it in contact with the ring gear, and that seems to work much better. Okay, so also I replaced and applied super lube to the Oldham coupler. This is what an Oldham coupler looks like. So again, the Oldham coupler is to interface the gearbox to the worm gear. So here it is. Here's the interface. This is the side that's going to the gearbox. This is the side that's going to the worm gear. And then there's this piece of Teflon that goes in between these two. So what's going on is if the gearbox and the worm gear are not exactly lined up, like they're not, the centers of them are not right, what's going to happen is this metal piece is going to slide in and out of this Teflon, and this piece is going to slide in and out of this Teflon. This is going to move back and forth as the motor turns the worm gear. So in my case, my Oldham couplers were worn out. They weren't really bad, but they had a lot of play in them, so I wanted to change them. And also, I was not comfortable with the fact that there may be a little bit of stiction there on these things. So I actually put the super lube in there. And again, super lube is a Teflon-based grease. So I felt okay about putting a Teflon-based grease on Teflon. I feel like that's probably okay. And the movement of these components inside the Oldham coupler was much smoother once I did that. And I saw another guy on the Los Mandes users group that really felt like that was a big deal, and I was influenced by that, and I believed it was a good idea. All right, so number 5, then you have to set the gap between the worm gear and the ring gear. So as you can see, there's these bearing blocks, and underneath this thing, there's a bolt that you loosen and tighten. But there's a gap here and there's a gap here. So what you do is you use a gap gauge or feeler gauge, and the idea is to get the gap set on these so that the worm gear and the ring gear are in close proximity to each other, so there's not a lot of backlash or slop between them, but you also don't want to be so tight that it stalls the motor. Now in the Los Mandes hand controller, what you'll see is you'll get this message that says RA motor lags, and that's if you got it too tight, it's stalling the motor because this is just too tight on here. So it was a little bit of a trick trying to figure out what the right setting is between these, and this takes some time to get this right. But in the end, you want the worm gear should move smoothly, but not have any play or backlash in it. That's the objective here. Number 6. Okay, so I line the motor with the Oldham coupler and the worm gear to decrease the movement of the Oldham coupler during rotation. So what this is, here's the motor and the gearbox. They mount on these threaded posts right here. But what you really want is this gearbox to be right in line with the worm gear. When I originally took this apart, there was quite a lot of movement of the Oldham coupler. I would say it was coming out maybe 1/10 of an inch when this thing would rotate. This metal side of the Oldham coupler was actually coming up about 1/10 of an inch out of the Teflon. And I was not comfortable with that. I wanted to get it so it was just straight on so I could not feel any movement at all of the Oldham coupler. But what you have to do in order to accomplish that is you have to take the gearbox and get a file and file out the holes on the gearbox so that you can move the gearbox around to get this lined up. So you basically file out the motor holes and you fill in the other side that you filed out with something. I just used some thick pieces of galvanized wire to fill in the holes to get this all aligned, and you tighten it up. Okay, now number 7. Okay, truth is truth. I'd like to sit here and tell you that this is just all wonderful and easy and no problem, but I actually spent a couple months doing this, and I redid it about 4 times before I was happy with the results. Number 2, I damaged multiple bearings during the process because I was probably just too rough with it. Number 3, I did get the motor lags message after initial adjustment, which wasn't good. It means I had the worm gear and the ring gear too close together. I had to redo it for that purpose. Number 4, I started out with 2 Belleville washers, and the people in the Los Mandes user group, their design is they showed 2 Belleville washers, but I could never get that to work. I had to change it to just 1. There was just too much tension, and the bearing blocks I found were not all machined exactly the same. And so in my case, I needed to only have one Belleville washer. And number 5, I had difficulties getting the bearings out of the bearing block, and I had to buy a new bearing block, so I actually damaged one of the bearing blocks trying to get the bearings out of it. It was stuck in there so hard I couldn't get it out. And number 6, I found that the ring gear actually had some high spots on it where the worm gear encountered more friction. And there's not much that can be done about that, I don't think, because, you know, no matter what you do, you can't machine something perfectly. But you know, Los Mandy is a great company. They're a U.S. made mount, and their workmanship is incredible compared to some of the other mounts that I've had. But even with their good workmanship, I did find a few high spots on the ring gear. No big deal, but they were there. And number 7, I did unfortunately get some grease on the clutch plates. And the clutch plate, let me show you real quick what the clutch plate is. You may not know what I'm talking about. You probably don't. This Teflon thing right here is the clutch plate. Okay, so the clutch plate is not supposed to have grease on. In fact, you can see some grease right there on the other side of it. The clutch plate is supposed to be dry and clean. So you take this off and you clean it with some alcohol and you put it back on. But in my process, I unfortunately got some grease on here, which made the clutch so it did not work. So it's just the axes were slipping all over the place. The clutch plate is supposed to hold it sturdy when you tighten it down. And that did cause me to have to reassemble it. So if you ever do something like this, just remember, if you're wondering about your clutch plates, they're supposed to be clean and dry. Don't let any grease get on them. Okay, so results. I'm going to show you the unguided results. I'm going to show you the guided results. So guiding is the process of locking onto a star and then sending correction signals to your mount to correct it if the star is not exactly where it's supposed to be. This is how astrophotographers accomplish long exposure images by using what they call guiding or auto guiding. So first, I'm going to show you my unguided. This is in the case where the auto guiding is not turned on. So you can use PhD2 Guiding Assistant. PhD2 is a program that a lot of people use for astrophotography. It's used for guiding your telescope mount, locking onto a star, like I said. But under the Tools menu, you'll find a thing called Guiding Assistance, which will turn off your auto guiding, but show you what your mount is actually doing. You'll still stay locked onto the star and tell you how bad your mount is without any auto guiding. So before I started this whole thing, this is what my right ascension axis looked like. So that's pretty ugly. And I was getting somewhere around 11 arc seconds peak to peak periodic error. Okay. Then after all my efforts, I was able to get down to about 4 arc seconds peak to peak. You have to try to ignore this drift here. That's another story, but the actual periodic error for the right ascension axis is right here. You can see it going up, you can see it go down, you can see it getting back where it started. And this peak to peak is about 4 arc seconds. Now, some of the other folks in the Los Mandy users group actually were able to obtain down to like 1 arc second peak to peak periodic error. I was not able to get, do that well, but there are other people who have been able to do even better with the same mount and tuning it up. Now, here are my guided results. So prior to this adjustment, I was typically getting around 1.5 arc seconds RMS error, which is not too good, because if your pixel is 1 arc second and your RMS error is 1.5 arc seconds, your peak error is going to be larger than that. Peak is like 1.4 times RMS, and peak to peak is 2 times that. So anyway, that's not acceptable. We're going to see, and I did see elongated stars in many of my images, which was disappointing. So when in my guided results, using the ST4 auto guiding port input, I got down to, in this test, 0.58 arc seconds RMS error, which is much better than 1.5, obviously. And then using pulse guiding, I was able to get down to 0.43 arc seconds RMS error. And this brings us to another topic. Okay, in the past, when I looked into this and I tried to understand what was the best thing to use, a telescope mount has, typically has 2 guiding inputs on it. It has an ST4, or it's also called an auto guiding port. And the other one is your pulse guiding input, which is usually your RS-232 cable or your USB cable or whatever you use to control your telescope mount for doing go-tos and things like that. As long as you have a driver that will allow you to do this, that is the pulse guiding input. So when I looked into this in the past, I convinced myself that ST4 auto guiding ports were the way to go. But more recently, I have been watching these Los Mandy podcasts and watching some of their videos on their webpage, and they are adamant that pulse guiding is the way to go. And they were right. So I tested this. This is actually the same configuration, the same night, just one after the other, ST4 and a switch order pulse guiding. I went back and forth several times, and consistently I got better results with pulse guiding than I did with the ST4 auto guiding port. And it's about 20%-ish difference, something like that. So that was an improvement. Okay, so here's my last slide. This is an image taken after the mods, and we're getting smaller stars and less elongated stars. This is M13, the globular cluster, and Hercules. And I'm pretty happy with the results. These are probably the smallest stars I have been able to achieve with this configuration. So I was pretty happy with the results. And that's about it. I'll have this presentation will be put on my webpage at www.holland-observatory.net. And along with my other presentations and many of my other astrophotography pictures, if you'd like to check out the webpage, feel free to do that. That's about it.
Hey, Doug?
Yes.
Real quick, could you also list your sources for your materials that you got on that?
Yeah, let's go back and look at all these. Yeah,
the lubes and the degreasers and the powder and
right. Let's talk about that. Okay, this gunk general purpose degreaser, I got that at Ace Hardware, but ironically they don't have it on their webpage. I was trying to get a picture of it the other day. I have no idea. It's actually at my Ace Hardware, but it's not on their webpage. The Super Lube, I actually got that at Ace Hardware also. The Derby dust, this is called tungsten disulfide, but it's also called Derby dust, but you got to be careful because there's more than one kind of Derby dust. Apparently the guys that make Pinewood Derby cars also use this stuff to make their cars really fast. But you can find it at a Derby dust, but you got to make sure you get tungsten disulfide WS2 powder. I can't remember where I got it, but if you do a web search on it, there are places you can buy it. Now, these bearings, I got these bearings shown here from actually Boca Bearings. You can see the thing here says Boca Bearings. They're in Florida, but I bought the Los Mandy replacement bearings on the Los Mandy webpage. Los Mandy has a very nice webpage where they list out all these parts, these replacement parts. It's one of the nice things about the Los Mandy mount. Made in the USA, you can buy parts directly from them. I got the bearings from them. I also got the, hold on, I'll tell you about that in a minute. Also got the this Oldham coupler, new from Los Mandy. It's on their webpage. Now the Belleville washer, that is from McMaster Car. And what you can do is if you send me an email, or I can find you the exact part number for that Belleville washer. And my email address is available at my webpage, www.holland-observatory.net, and I can find you the exact part number that I use for that Belleville washer. And I'm using the same one that the other guys in the Los Mandy users group use, and they've had success with that. I have no idea where I got the feeler gauge. I've had it since I was 18 years old trying to fix my car. I think that might be all the parts that I got. I think so. And if you want to know where I got the mount, I bought on eBay, the source of all good things. All right.
Doug, one other thing, when you said you looped the Oldham coupler,
yeah,
did you just use the lube or did you do the combination?
No, I didn't. I just used the lube only.
Okay.
My thoughts were that the Super Lube is a Teflon-based lubricant, and I thought it'd probably be okay. I mean, there's some serious problems. If you try to use the wrong lubricant on the wrong material, you can get yourself in a lot of trouble. And I'm not, since it was Teflon on Teflon, I was okay with that, but not the WS2, the tungsten disulfide. The other thing is an obvious question. Someone may be thinking, well, how much tungsten disulfide do I put in the super lube? That's unknown, because what you do is you squirt out some of the super lube and you kind of take a pinch of the tungsten disulfide and kind of stick it in there, kind of like cooking in a way. And you put it kind of in there and you kind of look at it and kind of guess, but I can't even tell you how much one to the other I use, but that's the way most people do it. They just kind of put it in there and kind of guess. But it is significantly better with the tungsten disulfide on metal parts. So anything else?
Oh, I'm sure I'll have tons of questions for you later.
Okay, yeah, and I know Trevor's actually has a Los Mandy G11 mount too, and he's going to be, maybe, but yours is actually already fixed up a lot, because the nice person that donated that mount and you got it from actually used to rebuild these mounts, and I think if I remember right, it's in pretty good condition already. So maybe, yeah.
Yeah, I do have a question about that. When I'm tightening the deck clutch,
Yeah.
I actually get it actually turns the whole deck. Is that normal?
Yeah, that's normal.
Okay.
You got to hold, yeah, you got to hold the declination axis with your hand and then tighten the clutch up.
Okay.
Yeah, that's normal. But if once you've got it tightened up, the declination axis moves easily, then there's two problems that can cause that. One is that you can have grease, because it could be grease on your clutch plates. The other thing is okay, let me see if I can find this. Okay. At the bottom of this pipe or rod or whatever you want to call it, there are several washers which can be bought at Ace Hardware also. So one of the nice things about this mount is you can buy a lot of these parts down at the hardware store. But these washers I'm pointing at right now actually can be bought down at the hardware store. If there's not enough of those washers between this nut, this Captain style nut, what will happen is this thing will come up and it'll hit the end of this bar and it won't tighten up. So what you have to do is you have to put enough of these washers in here to hold it off so you're still in the threaded area. In my case, when I got this mount, it did not have enough of these spacers in there. I had to go down to the hardware store and buy some extra ones, because neither the declination axis nor the right ascension axis would tighten up correctly, because there was not enough spacers in front of this this nut here. So if you have a problem with that, they're easy to find down at Ace Hardware, and you can space this out as far as you want. Okay, any other questions?
I think that's it, Doug.
All right, thank you. All right, so next up we have David Haviland with Star Party News. Take it away, David.
David, you have a go.
All right, that was really cool, Doug. I like that a lot. Okay, Star Party News for July. Get it to slide one slide. We had absolutely no past events. Sorry, that's just the way it worked out. But however, next Saturday, a week from tomorrow, we do have an event at the Hack Winery. History so far hasn't been very kind to us. Maybe this will be different. We don't know. September 17th, another Hack Winery event. October 7th, the trip to Fort McKavett has been moved. I got a recent email from Lisa asking about being able to move it, and said it's no problem at our end, and I'll have it later on. It's actually going to overlap the Occultations, I believe. No, not Occultations, El Dorado. October 15th, all clubs meeting, possibly at the HMNS, possibly still virtually. Leonard, myself, Tracy Gnoss, and Kavita of the HMNS Sugarland. We are still discussing the possibility of having some form of an A-Day at the George Observatory. November 1st through 6th, El Dorado. 4 through 7, the club's trip has been moved to here, so people could start out at El Dorado and have the option to finish at the fort. And then we finish up the year November 19th. At the winery. Things have been relaxing, and now people at the George, patrons that come for the prepaid tickets, are no longer required to wear masks, while the volunteers still are. I'm expecting Hack to kind of follow suit. There weren't a lot of people wearing masks at the last Hack event, even though it was severely clouded out. So we'll see how this goes as we go forward, and we'll see how the Delta variant plays out. And that is pretty much it. And sorry if I've used this before, but I think it still fits now more than ever. I don't know about the rest of you, but I've hardly got any scope time on my own. So it'll clear up any minute. And there's this one lonely little star sitting out there. Back to you, Doug.
Okay, Doug, you have a go.
All right. Thank you very much, David. And thank you again for being our Star Party chairman. All right, that's about it for tonight. Our next JSCAS meeting will be on August 13th, and we will have Using Planetarium Program Stellarium, and that will be Justin McCollum that will bring that to us. So thank you very much for attending, and hope you can join us again in August.